Okay, so we are going to look at a problem that reads, you are asked to hang some street signs for Greek Week. One sign, which has a mass of 50 kilograms, hangs vertical, and the house wants to hang it between two trees as shown below. There. The only string the frat has is to hang the sign has a breaking strength of 450 newtons. Before you attempt to hang the sign, you want to determine if you can use the string or if you have to go to the store and buy some new stuff. Is it possible to hang the sign as shown, or will the string break? So if the sign is happy hanging there, this is a state of equilibrium. The object, the sign, is not changing or translating at all. It's not changing its motion, therefore we're in a state of equilibrium. So let's identify the object of interest, that is our sign, and we're recognizing that we are in equilibrium. And what does that mean for us? Well, it tells us that the net force is equal to 0, and that's the net force in each direction, so that's going to be an important element. All right, so what do we do with a force equilibrium problem? Well, we need to do a force analysis. I need to see what the tension is in those strings to know if they're strong enough to hold the sign in that form. So let's look at the interaction on the object and then develop the free body diagram. Well, we know that the sign is experiencing the force of gravity between the sign and the earth. That force always exists. And so let's draw that force on a free body diagram. It points straight down, and we know it equals Fg or mg. All right, well, we have this rope. We'll call that tension 1. If we tie that piece of rope to the sign, then we'll call that tension 1. That's between the sign and, let's say, the right rope. And that's sort of pulling the sign in this direction, up like this. And we know that this angle, theta, is equal to 52 degrees. So it's showing us that is the angle relative to the vertical. All right, well, our third force acting on this object is this tension. So we'll call that tension 2. And that's between the sign and the left rope. And that's moving off in that direction. And we're told that this angle, theta, is equal to 30 degrees. Nothing else is interacting with the sign. There's no normal force because the sign's not resting on anything. There's nothing pulling down on it or pushing it. These are the only three forces acting on the sign. Okay, so we know the sign's in equilibrium. So let's continue our force analysis process. We will number each force and then break each force up into its horizontal and vertical components. So force number 1 is my force of gravity. It doesn't have any horizontal component, but its vertical component is equal to minus mg. Force number 2, well, that has both a horizontal and a vertical component. We have the tension of the rope, force 1, times, well, we have this is my angle, and this component is opposite my internal angle. If I want to use this internal angle that's given, I could use a different angle. I could use one relative to the horizontal axis. But I want to use this 52 that's given. It's opposite. So in this case, it's the sine of 52 degrees. And for the vertical direction, the tension times the cosine of 52 degrees. So it's adjacent to the vertical direction. Because I used an internal angle, I want to make sure about my directions themselves. I'm only using angles between 0 and 90, so I have to be explicit about the direction of that force. I know my horizontal component is positive, and my vertical component is also positive. All right, now I have my third force. So I have the tension of rope 2 times the sine, sorry, not the sine, got kind of on monkey mode. All right, so this is my angle. That's a 30-degree angle. It's an interior angle, so I got to pay attention to sine. and that's 30 degrees. The horizontal is the adjacent side, so that's the cosine of 30 degrees. But I know my horizontal component is pointing to the left. And then I have T2 times the sine of 30 degrees. Again, with an internal angle, I want to make sure my signs are appropriate. It's pointing in the positive directions. I think we're okay. Okay, well, we know that this object is in equilibrium. So the sum of the forces horizontal are equal to 0, and the sum of the forces vertical are equal to 0. So let's add these two up, and we end up with T1 times the sine of 52 minus T2 times the cosine of 30 equals 0. All right, and in this case, I have minus mg plus T1 cosine of 52 plus T2 sine of 30, and that also equals 0 because I'm in equilibrium. All right, well, I don't know T1 or T2. I do know both m and g. I'm given the mass of the sine at 50 kilograms. Let's remind myself of that over here. We're given that in the problem. So I have two unknowns. I need two equations with those same two unknowns, and I have it. So I can solve it, but I have to solve it as a system of equations. So my favorite way to solve systems of equations is substitution. So I'm going to do substitution of this relationship into this one. So I'm going to solve for T1. Bring T2 to the other side. T1 sine of 52 equals T2 cosine of 30. And then I'm going to divide by both sides by the sine of 52. And I end up with T1 is equal to T2 times the cosine of 30 over the sine of 52. Now, I have a tendency to get a little bit cumbersome in my writing, so I try to eliminate some of that cumbersomeness. So I'm going to take the cosine of 30 divided by the sine of 52 just to reduce that. And I end up with 1.099 T2. Now I can take this value for T1 and plug it in up here. So I have minus m, which is 50, times 9.8, plus, now here's my T1, that equals 1.099 T2 times the cosine of 52, plus T2 times the sine of 30, that equals 0. So, simplifying a little bit, I get minus 490 plus, well, 1.099 times the cosine of 52, 0.6766. I'm keeping a lot of significance just to get closer to the rounded number that I'm going to ultimately use. So plus 0.6766 T2 plus the sine of 30 is equal to 0.5. T2 is equal to 0. So I just put all of these sines and cosines and this multiplication into a number. Now I have two values of T2 at minus 490 plus 0.5 plus 0.6766, 1.177 T2 equals 0. Now I can solve for T2. 1.177 T2 equals 490. T2 equals 490 divided by 1.177. And I get T2 is equal to 416 newtons. So the strength of the rope is 450 newtons. So I'm okay, because that T2 is going to be 416. But what about T1? No, it's going to be a little higher because I'm multiplying it by 1. So let's use that to plug in to my relationship for T1. So T1 is 1.099 times 416 T1 is equal to 457.5 newtons. No, it's not strong enough if the rope, let me just double check that rope, if the rope has a breaking strength of 450 newtons. So, we knew that we were in a state of equilibrium. We solved the problem for that state of equilibrium, recognizing that means the horizontal and vertical dimensions, the forces sum to 0. We're recognizing some of that angle issue, being very attentive to those angles and making sure that we are within the proper angles. And then we solve for each direction. Now I happen to just notice an error between my picture and my solution. So I drew the picture at 32. I solved it as if it was 30 degrees. So I apologize for the mistake in my picture. That's not good. But the process is certainly the same, and we will have the problem read and reflect that it is indeed a 30-degree angle instead of 32, so that our solution is consistent. For extra practice, you can go ahead and see what it would look like with 32 degrees. Same process, but would the sign hold? And could you adjust how you hang it so that you can use the string you have? All right, good job.